Welcome everyone. In the last lecture, we have seen the relations between the various material properties of an isotropic material. And we have, prior to that, we have also seen what the anisotropic material properties look like. Essentially, we had 21 elastic constants apart from density for an isotropic material, for an anisotropic material. Whereas for an isotropic material, we had two elastic constants and density. So how does one go about measuring the isotropic constants? Mathematically, we found the number. Isotropic will have 2, orthotropic will have 9, anisotropic will have 21 constants. But how does one go about measuring them? So that is what we will see in the next few minutes. So for isotropic materials, as we have seen, there are a set of parameters which were defined depending upon how you want to write the equation. First one is Young's modulus E. Next is Poisson ratio nu. First parameter is lambda. Lambda is this. And second Lamé parameter is also called as shear modulus, and it is indicated by mu. And we also had bulk modulus K. Right? And among these 5 parameters, there were only 2 independent parameters. Like we did write E as a function of lambda and mu, and nu as another function of lambda and mu. And we also had Young's modulus as another function of E and nu, right? So essentially you have 3 independent parameters. So if you find 2 of them, which means we know the remaining 3. So how does one go about identifying these elastic constants? Easiest way is the tension test. Okay, it's not like this is the only method that can be used to identify these. For example, if you have for an anisotropic material, we already know that the number of constants are 21. How does one measure all these 21 constants, especially for a triclinic material? The technique used is one can use various kinds of techniques. One of them is ultrasonic wave propagation. And in that, there's a special technique called RUS, resonant ultrasound spectroscopy. So in using one technique, using one measurement, we can identify all the 21 constants. Okay, using just one experiment, one can identify all the 21 constants. And the same method can also be extended for orthotropic, isotropic, and different kinds of materials, transversely isotropic. Okay, tension test. Why are we discussing it? If there is a technique which can identify 21 constants, 2 things. One, the theory required to understand this is beyond the scope of this course. So that is why we are not looking at this particular technique. But otherwise, tension test. Why are we using tension test? Because it is quick and easy to implement. Okay, RUS, you have to have an understanding of theory, then the inverse numerical optimization, and of course the experimental data. Either first the experiment, then the theory, and then the inverse numerical optimization. So it is a little more involved experiment. That is the reason we are not discussing that in this course. So let us see what this tension test is and how it is done. We'll start with the instrument. This is a standard, this is one form of a standard instrument which is used for tensile test. Typically, it consists of 3 major parts. First are the jaws. These are the 2 jaws, and in between them is the sample. Right? Typically, one jaw is fixed. It's the lower jaw which is fixed. So this is the reference frame. This is fixed, and it is the upper jaw and the upper jaw assembly which keeps moving up or downwards. Okay, this is the first set. Then the second one is the sample itself, and the third one are the measuring entities. So we will see what it is. So a typical machine of this kind is often referred to as a UTM, or universal testing machine. Why is it universal? In a minute we will see. Or it is also called as material testing systems, MTS. So it can basically, this machine can do a variety of tests. In all these tests, the upper jaw will be moving upwards or downwards, or it'll move and stay there. Okay. So depending upon how the motion of the upper jaw is, the test is given different names. For example, in tension test, if I look at the position of the upper jaw, if I call it as X with the time, in tension test, it is like this. You're continuously increasing it. Whereas in case of fatigue compression, the position of the upper jaw is, it goes up and down, up and down, up and down. That way your strain is also sinusoidal. Likewise, there are two other kinds of tests where it is called as creep and relaxation. In one case, it starts here and it slowly relaxes. In the other case, you suddenly give an increment and you maintain it. So these are the four common kinds of tests. Okay, so that is the reason it is called, this machine is called as a universal, because it can do these four different kinds of studies, each of which have different micro mechanisms. Okay, so that's the reason it is called, it was given the name universal. Universal in the sense that you can do these four kinds of tests. All right. So we will stick to, for now, we will try to stick to, we will confine ourselves to the tension test. So instrument, now we know what it is, what it can do. The second thing is sample specifications. So it's not like you pick up any sample of any shape and you stick it in the jaws and perform the test. There are certain standards, mainly because if person one is doing a measurement on a sample of steel and person two is doing a measurement on another sample of steel, if the properties of the same sample, let's say I consider stainless 304, the properties of stainless 304 will remain the same or should remain the same. The only difference that one can get is in if there are differences in between the chemical composition of the sample or in the geometric shapes of the sample, or if the standards are not adhered to. Okay, one cannot measure properties on, say, same stainless steel sample of this shape, and in one case a sample of this shape. Here there are more other structural effects. Okay, why cannot I use this shape to measure it? Well, you can use it. It's not like you can't use it. Just that the properties which you get are also dependent on this structure. Okay, so it's more like, it becomes more like a metamaterial rather than a material. So in order to avoid all these kinds of shapes, people have come up with standards. The common standards are, every country has its own standards, but one that is universally accepted is this ASTM standard, American Society for Testing Materials. They have come up with this standards for metals separately, ceramics separately, polymer separately. And in each case, let's say we pick up metal. For metal, if I have to do tension test, there is one kind of specification or a standard. What does that standard do? What does that standard have? The standard has the following. It will sometimes specify the shape. First, it will definitely specify the shape, and it will also shape as in rectangular or cylindrical. Okay, so let me draw the actual shape. Let me erase these. All right, so what is the shape? So the shape is, let me first try to draw a clear rectangular specimen. So this is a dog bone shaped sample. Just don't call it dog bone sample. Dog bone sample implies it's a sample from a dog bone. And this is a dog bone shaped sample. Likewise, you can have the cylindrical one. This is axisymmetric. Right. So shape is one which it will specify, or rather, if you have to choose a rectangular cross-section shape, this dog bone shape. Both of these are termed as dog bone shapes. Either it is rectangular or cylindrical is something which the user can choose. Then the second thing it does specify are the dimensions, spatial dimensions. Okay. So this is the gauge length. Gauge length is the region where the stresses and strains are uniform across the length and cross section. So this is the gauge length region. Okay. This is the region over which the stress and strain are constant across the cross section as well as the length. Okay, so this is the gauge length region, and this is the grip region. Okay, this is going to go into the grips of the UTM. Right. So typically ASTM standard will specify shape, dimensions, and sometimes also the temperature conditions, temperature and pressure. What we are doing is a uniaxial testing. So typically there is no external pressure. The external pressure is simply atmospheric pressure. Sometimes you also put this sample in a pressurized environment. It is called as triaxial testing. What we are doing is we are pulling the sample along one axis. So it is uniaxial testing. So if you have triaxial testing, then there will be more parameters involved in. Can I write it clearly? Uniaxial test. So if you have an externally applied pressure, then it becomes a triaxial test. And in that case, there will be more specifications. Okay. Like as I said, cylindrical and rectangular are the two common shapes. All right. So if one wants to measure a sample properties, it is advised or strongly recommended that one sticks to these standards. Okay. The shapes and sizes are do vary for and also based on the type of test. Here we are specifically talking about tension test. If your test is fatigue, then you may want to have a different kind of sample. Measurements. So we had seen what the instrument is, what should be the sample specifications, and what should be the sample specifications. Right. And let's see what is it that we can measure. First is the force, which is load cell. We have only two entities to measure. Either it is force or displacement, because using force, we can calculate the components of stress. Using displacement, we can calculate the components of strain. And specifically, it is the normal stress and the normal strain. So force is measured by most often, it is measured by the load cell. There will be some machines where they would want to measure it using a series of other mechanisms. But most commonly, what you see here is the load cell. Okay, that's the load cell. So the displacement, so this is the sample, right? I'm going to idealize the drawing instead of putting the dog bone shaped sample. Let's say I'm pulling it here. Right. Now strain gauge, one can put a strain gauge along the length. Or if you have a small enough strain gauge, you can also put it across. So the one which you put across will measure, let me call this as Z and this as X. So the strain along X and Y can be measured by this first one, and the strain along the axis is measured by the second strain gauge. So this is one way to measure strain. So using strain gauges, one can measure the strains along the longitudinal as well as the transverse directions, in the transverse direction. But however, the flip side to strain gauge measurements is that one has to always stick the strain gauge to the sample. It is a contact based measurement. It is still in use just only because it is reliable. The second one is what is called as an extensometer, which will also measure again, which will also do what a strain gauge does. Just that instead of putting it as a over an area, you simply stick it around two places, and this is your device. So this will measure what is the change in length in the gauge length region. So extensometer typically measures the axial strain only, or changes in displacement along the axial direction. A more common and increasingly used technique is DIC. DIC is digital image correlation. DIC is digital image correlation. Digital image correlation using photographs or a series of photographs or at least two photographs, one can identify what is the longitudinal as well as the transverse rates. So that is the, and this is non-contact method. So that is the major advantage of using a, when I say camera, it's an optical camera. Optical camera is the one, the cell phone camera or the DSLR kind of cameras. And there are also laser-based sensors. Laser-based sensors are avoided mostly because they're expensive. But it is again non-contact and precise measurement. It's just that they're among all this is the most expensive and this is the most easiest one. And due to the availability of cell phone cameras, this also is in practice. All right. How does one do this experiment? We know that there are only two variables, force and displacement. So imagine this, you're holding the writing pen and you are stretching it. You're holding it on either side of your hands and you're stretching it. Are we applying force or are we applying displacement? Or when you sit on a chair, are you applying force or are you applying displacement on it? In practice, physically, it is both. They are not independent of each other. Okay, so when you are applying force, there is displacement which is occurring, and when you are applying, when you think you are, pressing a balloon by 2 mm or 1 centimeter, you may be controlling the way you are compressing the balloon by how much you compress them. However, at the same time, you are also applying force. Okay, so these are coupled entities. So the way you do is you control one of them. As a user or as the operator, you control one of them. Let's say I control force. I will feed to the instrument that I will measure. I will do this experiment. I'm going to pull the sample at the rate of 5 newtons per second. Every second, I'm going to increase the force. So if I plot force with force applied by the grips, force with time, so I'm increasing the force like this. This is how I'm going to apply the force. Or I can say the displacement is, I will control the displacement with time. It is like this. Or I can, one can, I can as well say it is some other displacement. All right. So there are two ways in which you control them, control the experiment. And some users also call it as strain control, which is incorrect because strain does not have a unit. This is displacement units. 3 mm per minute is basically displacement control rate. Strain does not have a unit. So, but people do call it as strain control, which is a loose term. What do you measure? You measure both force and displacement. Why do you, even if you do a force controlled measurement, your load cell will measure the force. So you will know ideally this is what you want. So you may end up getting something like this with some error. Experiments will always have deviations. What do you calculate? Using the force, you calculate the axial stress. Using the displacement, you calculate the axial strain. right? And you measure displacements in both directions. So you'll also calculate the lateral strain. Right. So using force, you calculate this. Using your displacement measurements, you'll get these two quantities. How does one calculate this? Axial stress, axial strain. So let's quickly wrap this up. Axial stress, you are measuring force, you know the cross section. So you know F, you can calculate F by A, and this is nothing but the sigma 11 or sigma XX. Axial strain is measured, which is delta L is what you measure, you know L, which is nothing but the epsilon longitudinal, or now that we know that it's a tensor, I'll put it as epsilon 1. Lateral strain, delta D by D. Oh, I'm sorry, I'll use a different D because D we have used for displacement control. Delta D by L0 D0 is nothing but epsilon 2. And we know the relation Poisson ratio is epsilon 2 by epsilon 1. Since if we are increasing delta L, then delta T automatically becomes negative. So I will retain that minus sign. So these two are measured, which means Poisson ratio can be simply identified by taking the ratios of lateral to axial strain. You know the Poisson ratio, and for a one-dimensional experiment, sigma 11 is epsilon 11. We have calculated this, which means you can identify the value of Young's modulus. So once you know the Young's modulus and Poisson ratio, the remaining parameters, lambda, mu, and the bulk modulus can all be evaluated. So using a simple tensile test, we can measure all these 5 quantities. Okay, that is why it is commonly used. There are more sophisticated techniques which can capture various other kinds of parameters. Also, when I say other kinds of parameters, for more complicated materials such as orthotropic or the triclinic materials, just that technique involves understanding of higher level concepts, and also the experiment requires a little more sophistication. All right, so this is the way you identify elastic constants of a material, and all these constants which we are measuring are not functions of frequency. They are at, you can call it as DC test. They are not dependent on time. Okay, the speeds at which we are pulling. For example, let's go back to that slide where we are controlling things. So these speeds, for example, 3 mm per minute is supposed to be a quasi-static. This test, the tension test, which we have been talking all through this lecture, this test is performed in a quasi-static mode. Okay, there is no concept of time. Although we are pulling it, this is pulled at a very slow rate. Okay. If I have to pull the sample at 3 meters per minute, I mean, this is basically a very rapidly stretched sample. That is not the kind of test that we want to do while measuring these properties. We are doing it as a slow test. It's a quasi-static. You're pulling it slowly. Okay, if as the strain rate or the displacement rates increase, Young's modulus can become a function of strain or strain rate. So does Poisson ratio. Okay, those are not the ones which we are looking at. We are looking at quasi-static test, and the typical tensile test is performed in a quasi-static mode, which is at a slow loading rate. All right. So we will end with this part here. I'll see you guys in the next lecture.